All instructions have constant execution time, which might fit them for a separate idea to some extent. And there's zero timing dependency between instructions. Sometimes you have some, for example, if you have a standard pipeline with instruction cache and a data cache, if one instruction misses data cache, one instruction misses instruction cache, then you have a dependency between, timing dependency between those instructions. In our case, actually, with this method cache, we even miss in the same stage. So there's no, as far as I know, there's no timing dependency, any instruction. No, there is no. The load use dependency is scheduled by the compiler. Good, the compiler is, we used LLVM, we fully support Patmos. We have this instruction for working with the stack cache. You have to ensure that data is in the stack cache and this stuff. We have support for the method cache. So method cache is that full methods have to fit in the cache. If a method or function is too big, the compiler splits it and tries to optimize the size towards this cache. And there is an integration with the absinthe tool AIT for optimizing for the worst case execution time. Yes?
So, from what I know, the absinthe tool, it's actually pretty labor intensive to construct a processor model for it to work. So, how is the processor model specified?
In the AIT itself? I have no idea, it's closed source.
Sorry?
It's closed source, so I don't know how they specify it. It was done by Absinthe.
Oh, it was done by Absinthe?
Yes, they were partner. They did it.
I see. Okay.
So they actually had to change the tool because they had no support for predication. Yeah. They had very weak support for VLIW. So actually they got something into the tool as well. No, it was actually, when you look at the visualization from this worst case analysis, it's way more complicated than the simple pipeline needs to be.
Yeah.
Yeah. So we deliver flow facts for AIT. Flow facts is like loop bounds, for example, or targets on indirect branches for switch case statements. And the compiler also does single pass code generation. I have one slide on this as well. Worst case analysis, in the meantime, we actually have 3 tools, more or less, available. So besides having Absinthe in this project adapting their tool, we had a PhD student who did the worst case analysis tool for YOP as a master thesis. He actually did it again, a worst case tool for Patmos, so under the radar in the project, which is open source, so that's nice. And the French group around Isabelle Pouot, they have a worst case tool, it's called Heptane, and one of her students also ported Heptane to Patmos. So it's nice that it moves a little bit.
So these were also done, like the Platin tool was done by a partner on this project?
The Platin tool was done by a student in Vienna, so it was partner of the project.
So this was a big EU project?
Yes, it's the start of it, yes. The Heptane thing happened just last year. They just picked it up, Patmos. And it would be nice if more of these open source tools and go to Patmos and yeah, good. So we had support for Patmos I, so that's basically what I just mentioned before, so the AIT tool had to change. And they had simple method cache analysis. I think they did it wrong, but in 3 years you cannot communicate everything. So they've integrated stack cache analysis. We have both in our Platin tool, but we don't have data cache analysis in the Platin tool. That's where the Absinthe tool is very strong, doing data flow analysis and then can do data cache analysis, which is a very hard problem. Yeah, single pass programming. This is what came from Vienna. Peter Puschner was thinking about this and has done a little bit of work, and then he managed to get a little bit more done on this within the project. Single pass is that the program has only one pass through the code. That means in an if-else condition, you're executing both parts of the code. In a loop, you're executing until the maximum iterations. But then you predicate which path you take or not. So to support this, you have to use predicated instructions. And in that case, a theory is that you can just simply measure the execution time because it's constant. It works with reasonable pipeline, it works with instruction cache, it's broken with data cache. Normal data cache does not work with single pass code because you can have, sorry?
It doesn't work in the sense that it doesn't give you constant execution.
Yes, exactly.
But it does work.
I mean, the code is executed, but the idea doesn't breaks because you have some data-dependent cache misses. Instruction cache works. If you only pound pass, then it's fine. There was one PhD student who did even use this knowledge to prefetch, because the path is fixed. You can do that, like similar to this memory access thing that you showed us with these 4 processors. Where you had a small program in the memory controller. And you can do the same idea in prefetching. You have kind of a small program running in a prefetcher. Yes, and it needs predicate instruction, which we built actually for this idea. And actually, one PhD student did a compiler transformation pass, which transforms programs into single pass. Not all programs, of course. They have to be bounded loops and this stuff. No recursion. Good. What else on software? So we had 2 projects on porting and operating system, but sadly both of them single core. That's not so exciting for a multi-core processor, but it helped to run some user code. We had one cooperation with Augsburg, porting their multi-core operating system to Patmos, which was the last work of a postdoc, and then he moved to industry, so it's a dead end as well. But we have some tools for our network on chip. We have a library, user library, a scheduler generation for your application. Good. That's end of the software part. And what I see the main action is in this project is actually communicating between these many cores. How the data is moved around, message passing or different ways. And we want to keep as much as possible the data which we communicate between the cores on chip, because going off chip is simply very expensive, is harder to predict, so on. Yeah, so what is the current way how to share data in our laptops we have here? You allocate your data in main memory, you share them, protect them via lock, and then your level 2 cache currents protocol actually do the real movement between your data. If one processor writes, the other one reads. You need visibility rules when your writes get visible, but they stay mostly on chip due to just cache currents protocol. If the data you share and communicate fits on your level 2 or level 3 cache, then you don't go off chip. But you know, this doesn't scale very well. This cache currents protocol is a many-to-many communication, and it's, I would say, hardly time predictable. Let's say hardly instead of no, but it's very hard. Good. What our approach is, we do a static arbitration for time predictability. This is this TDM approach. This pops up everywhere in this architecture, maybe because I've spent too much time in Vienna at the Corporate Institute. I mean, it's a simple solution, and it works. Yes, and we have actually this platform to explore different schemes. So we're playing around with network on chips. We did 2 network on chips, 2 different, actually 3 variations, shared SPM and so on. So what do we have actually, what we could explore? So of course we can start with shared external memory. That's a starting point. You can try to make this time predictable with using TDM for example. We built a network on chip for message passing, which is a different programming paradigm. People are not so happy with message passing. They have to think more about what they communicate. Then we have shared on-chip memory, which is at least way faster than going off chips. And we built a distributed shared on-chip memory where actually you have local memories at the cores, and then you have a network on chip that does your read and write, still time predictable. And then the shared memory with ownership I've presented, I think, 2 weeks ago. Network on chip. So people often throw everything on a network on chip. So they have processing element, memory element, accelerator, whatever, and they all share a mesh-based network on chip. But actually, there are 2 types of traffics. One traffic is between the cores, which is a many-to-many communication. And then it has traffic from all to one shared memory. So very many projects combine this into one NoC. And we decided relatively early, this is 2 different traffic streams. We will build 2 kind of NoCs optimized for each traffic. And we were aiming for globally asynchronous, locally synchronous implementation, because large chips, you cannot have a single clock domain. So the idea is that the processors run in their own clock domain, maybe it's a memory controller, and then we have an asynchronous network connecting to this. And the interesting thing in this project is, how can we still have this time predictable when we have an asynchronous part in the hardware? What I learned in this project, a new term, mesosynchronous clock domain. Do you know what mesosynchronous means? I used to. So we have these synchronous domains here. We have an asynchronous domain here, packet switched, time division multiplexed network, time division multiplexed even is asynchronous. And then we have on the borderlines these network interfaces. Mesosynchronous means they're running from the same clock. They can be off with a phase. They can even be off with 1 or 2 clocks, whatever. Meaning the reset to start those is off by some time. But because we have a same clock source, the production rate and consumption rate of tokens is the same.
I thought that was called isochronous.
I have to ask Jens, he's a master of the asynchronous world. Anyway, so we did experiments actually starting this thing, actually those in 1 clock domain. Even off by more than 1 clock cycle, and then running a TDM-based schedule here. And because we have here flexibility in buffering, it was still running. So they were running schedules a little bit off, but it worked out because the sources trigger when the tokens flow in. You start with you have to fill it half full, these buffers with tokens, and then you start on, and then you can tolerate someone is pushing a little bit earlier or getting tokens out a little bit earlier. I think this was for me the most surprising result. Using an asynchronous structure, but still using here around a static TDM, time division multiplexing schedule, and this still works.
So where does the clock for the mesosynchronous interface come from? I mean, it's not the same as the CPU clock.
Well, that's a full picture, but we use the same.
So all the CPUs were driven off the same clock?
Yes, in our experiment, yes. But due to phase differences, could be off by phase. Due to delays on the reset line, could be off by more than 1 clock cycle. We enforced it with that someone is resetting 1 clock cycle later, starting the TDM cycle. This global scheduled TDM schedule 1 clock cycle later, but it could still be tolerated to this asynchronous elasticity here with 3 buffers per connection, or 5, we played around. The more buffers you put in here, the more you can tolerate being off by something. Yes, so I've mentioned this before, I think. So message latency bandwidth depends on the schedule. Most of the time we do an all-to-all schedule because it's simple. Topology, of course, and number of nodes. And when you think all-to-all schedule is a big waste of bandwidth, then I say yes, but it's a very cheap. Actually, this TDM NoC is a very cheap implementation. You don't have any buffering except your pipeline stages. You don't have flow control, and these router structures are very small compared to other networks, also the network interface. So we are wasting bandwidth very cheaply. And the all-to-all, when you, let's say we build a 64-core system, and then have to schedule an all-to-all communication for everyone to everyone, which is 64 multiplied by 63, right? That's what is that, roughly? Well, 500 connections? No. Something around. So how many TDM slots do you think we need for this? You have to think it's actually, no. You have a lot of these links actually. When you do a BTORS connection, there's a lot of bandwidth available. It looks at most, so there's one limit for sure, which is I/O limitation. If I want to send out to 63 other ones, I need to have at least 63 slots or clock cycles, whatever it is. But most of the time it is. We didn't find optimal schedules. We found some until 5x5, but larger ones we didn't find optimal ones. But they are until 64, they are limited more or less by the I/O bandwidth.
So when you confused switch So TDM is easy to understand if you have a bus.
Yes.
You don't have a bus.
No, it's a network. It's a pipeline TDM. I tried to build a schedule by hand for a 3x3. It was impossible for me. It means you have a TDM slotting or everywhere going on. But you have to make sure, okay, if this one moves in clock cycle 1, in clock cycle 2 it has to move there, and so on. So you have to schedule all passes interleaved. It works out.
Sounds like a very difficult schedule.
When you do simplify, that everyone, first of all, we do a bitorus, which goes through turn, so it's a regular structure then, when you do bitorus. And if you agree to do everyone talks to everyone, then you can find one schedule that's executing the same thing on everyone. If a packet goes north here, it goes north here, 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 here. Because if everyone talks to everyone, it's a regular structure, you can find one schedule which is regular and does the same for all. And we find almost optimal schedules in minutes. It's not so. If you don't want to say. We try to find with an ILP formulation optimal schedules. And one was found for 5x5 in 3 weeks. So this is clearly a problem. But you don't need to find the optimal one. You need to find some schedule which is good enough.
Vague recollection of a project called Nearnet or something like that. Way back in the 90s, they was doing something similar.
Okay.
You run across it?
No. Okay. Yeah, I mean, I think a lot in the network on chip world is repeating stuff we had before on the network between computers. So you're repeating all these things. The technology constraints are different. So this makes a difference. So we can, for small systems, we can actually do a clocked version where you have exact timing and everything. Good. Yeah, okay, I didn't need, you know what TDM is. Yeah, the Argo is the name for that one. It's a TDM-based NoC. We have a 3-stage pipeline router. We have variable length of packets at the end. And the network interface is also running on this TDM clock, and this one drives, as I explained before, with this synchronous clock, the asynchronous network of routers. And we have also a DMA machinery, so that the message actually gets out of the Scratch local memory into the network, and this one is also time shared because it also knows about the schedule. The schedule goes up till the Scratchpad memory, which is different. Okay, this is a 3-stage router, a link header processing unit. We have a route in the header, and then a crossbar is a big word for a bunch of multiplexes, and then a pipeline stage, and then it goes off to north, south, east, west, and local. So it's a 5-port router, 5 input, 5 output. And let's contrast this a little bit to classic work by Keith Cousins, who was in the project as well. So his ESA Real network, maybe you stumbled across it. He has done TDM-based networking 10 years, 20 years ago. But they're doing TDM-based here on the network, and then they have flow control, because we have a Scratchpad memory DMA, which actually has to have flow control here, and they're using TDM only here. So we're moving the Scratchpad memory from the process and the DMA machinery into the network interface, which means this DMA machinery knows exactly about the schedule, and it can actually be shared with all traffic flows, because it's already doing TDM here as well. Good. The same idea we do in memory access. So we have a memory arbitration from the cores to the main memory. There's a many to one. You see this is a tree form. But because we know, okay, we're running kind of conceptually or practically the TDM schedule at the memory controller interface, where everyone gets a slot. Because all processors have the same notion on time, then you can actually map this schedule into your network interface locally. So you do local decisions on your schedule. You know at which point in time you're allowed to insert a packet. And you don't need to have a central arbiter. And even If you know this one, then you can actually make this merge simple OR gates. We don't do any decision here at all. It just flows because it goes only when it shall go. And the return path is also 3. And you know, you can actually send broadcast all reads to everyone because you actually also know when to receive your read return. You can just not listen when something else is coming. Yeah, and then here is a symbol. Let's say you have 2 cores you want to read, core 0 reads, core 1 reads, and then we have this slotting which moves with the pipeline along in time. You see, slot 0, this core 0 is allowed to do a read command, then it gets out the network controller on the memory, and the memory you get to read back, and then it moves up the pipeline in the response. And even if this one response comes after the read is accepted from the second one knows I have to not listen until I'm here. It's just listening to counters.
I guess you put that, you generate some sort of control code for the router, or how does it know to not listen?
Because this, okay, I don't know. This timing is fixed. You know it at construction time. You know how many pipeline registers you have. You know your latency of your memory controller. There's no flow control at all. And you know it takes 17 clock cycles until my read data come. And during this 16 clock cycles, I'm just not listening. So it's statically scheduled. And this is also possible with an SDRAM controller. So we reserved 1 TDM slot for refreshing, for example. So we don't have refresh getting in the way. Good. Shared Scratchpad memory. We talked about this a little bit before. So local Scratchpad memories are very popular, but Kelre showed us the path to shared Scratchpad memories. It's also convenient to have shared Scratchpad memories instead of a level 2 cache. And of course, we do TDM-based arbitration here as well.
So yeah. You said you reserve a slot for refresh, but these are all static ones, aren't they? Why do you need refresh?
No, we have also an SDRAM controller as well. We use SRAM and sometimes SDRAM when it's too small. So we have an SDRAM. We have one configuration with an SDRAM controller where we reserve 1 TDM slot for refresh.
But you need deterministic latencies for
Yes, we have closed page policy. We have our own DRAM controller as well, which works closed page policy. A very simple one. I know there's a lot of work, use some SDRAM work, and Benny Orkinson has made a PhD in the postdoc out of memory controllers, which was originally part of the T-CREST project. There was also a big project on a semi-dynamic, time-predictable SDRAM controller with rebuilding the commands and all this stuff. But I'm talking more on the simplistic ones. So if you do multi-core Scratchpad memories, besides having this external tree, but then this kind of Scratchpad memories ownership, and then we also have the concept of owning a Scratchpad memory, so you can reduce your access time to 1 or 2 clock cycles when you know you own it, and then you move it on the ownership to someone else, and then we have a pool of shared Scratchpad memories. This was a recent addition to our platform. So it just shows we have one multi-core framework. We can compile multi-core programs, we can boot them, we can download the stuff, and then we can start playing around with other communication tools. Let's see. We've also worked on hardware for locking this stuff. Okay, I'm coming to an end. So if we want to use T-CREST, and I hope it gets picked up a little bit. So it's BSD license, the 2-class license, which is the easy one. You don't need to reproduce your copyright. It's on GitHub. And we can live with only free tools. Doesn't mean open source tools, because for FPGAs you have to use closed source tools, but they are free. Yeah. So as a summary, I think we need new computer architectures for real-time systems, for time predictor systems. where the WCET analysis and or repeat table timing, which is more your direction. Are you trying that one?
Yeah.
Yes, good. Is important. Average case performance not so much. And the T-CREST thing is not just a processor, it's a kind of a platform. With the processors, with network on chip research, it was actually the most action during the 3 years was on the network on chip. We had some work on memory controllers, compiler, WCET analysis. Yes, and I would say T-CREST is for multicore communication research. For example, how to program these things. I don't know, right? We have just cores and we have a message passing mechanism. We can set up a message, say, okay, please move on, and this goes. And how is this mapped to a time predictable programming model, which hopefully maybe in our current work gets at some point to this multi-core thing. Good, thank you. That's it. Okay.